So what I'm going to talk about is joint work with my former postdoc, Mikhail Fountoulakis. And I will talk about the Laplace operator of random simplicial complexes. So let me start with the graph Laplace operator for graphs, and I'm going to talk about, I'm going to focus on what's called the combinatorial Laplace operator, which is defined as the difference between a diagonal matrix which contains all the degrees of a vertex of a given graph G, minus the adjacency matrix of G. And one quantity we're interested in is the smallest positive eigenvalue of the Laplace operator of delta G, and this is called the spectral gap of G. And this quantity is quite important because it has to do with the structure of a graph. And one of the first results that relate this quantity to the structure of a graph has to do with what is called the Cheeger inequalities. So it was proved back in 1985 by Allen and Millman that this is bounded from above by essentially quantity which tells us how set expands. Okay, so we have this ratio here, which essentially counts the number of edges going out of a set, normalized by the size of the set times the complement, multiplied by n. And this gives rise to what's called Cheeger inequalities, which actually bring to a discrete setting inequalities that were proved by Cheeger a bit earlier for Riemannian manifolds. So actually, the inequality from the previous slide implies that the spectral gap is bound from above by the minimum of these quantities. And it's bound from below as well, but the square of this quantity of h of g divided by essentially something that's proportional to the maximum degree of g. So in particular, if we take as a set A here a vertex of minimum degree, we have this inequality that the spectral gap is bounded by the minimum degree times a quantity that is almost 1 if a graph is large. Okay, so let's keep this the back of our minds and move on. So what I'm going to focus on is higher dimensional generalizations of the combinatorial Laplace operator in simplicial complexes. Okay, so what is a simplicial complex? Basically, is a set of subsets of a given set. Say we look at a finite set, vertices labeled from 1 to n, that is downwards closed. Okay, and it's called d-dimensional if the largest cardinality among these subsets is d plus 1, and a subset in this set of subsets is an r-dimensional phase, or an R phase simply if it has size r plus 1. And we're going to be noting by k with superscript r the set of all r-dimensional phases of k. Okay, so here, in order to define the Laplace operator, we need to develop a little bit terminology. Okay, and in this context, we need to consider orientations of the phases. So if we take an R phase and say, assume that the elements of the R phase are kind of ordered, then we consider two classes of permutations of the members of this phase, namely the even permutation and the odd permutations. And the even permutations correspond to the positive orientation, whereas the odd permutations would correspond to the negative orientation. And we denote K with subscript plus minus instead of oriented faces. In particular, if we have K plus minus R instead of oriented R faces. And what we'd be interested in, and basically the functions to which the Laplace operator would be applied, would be what we call R forms. Okay, and R forms are nothing but antisymmetric functions on the oriented faces. Okay, and when I say antisymmetric, so an R form is a function on the R faces, such that the value on one orientation is minus the value of the function of the opposite orientation. Okay. So now on these forms we define two operators, namely the boundary operator, which takes a J form and sends it to a J minus 1 form, which is defined things like this. So you look at you take the sum over all vertices that complete the J minus 1 phase into a J phase, and you sum the values of F over these, and the co-boundary operator, okay, which sends J phases to J plus 1 phases. Okay, so in this case, if you take a J plus 1 phase, this is the alternating sum of the values of F on subphases of sigma. And finally, the Laplace operator, the combinatorial Laplace operator in this case, is defined as an operator from a set of all d minus 1 forms to a set of d minus 1 forms. So if you remember, the Laplace operator in the graph case was sending functions on the vertex of a graph to functions on the vertex of the graph. So here it generalizes to d minus 1 forms as defined as this.
Sorry, Nicholas, there is a question in the chat. Maybe you want to take a quick look, if it's convenient, or I can read it out.
So are you talking about the graph case, or what? Which case? I mean, I don't think I understand the question here. And
sorry. So
no, yeah, no, it's not necessarily connected. No.
Okay, got it. Thank you.
Right. So going back to the definition of the Laplace operator. So this is defined as a sum of two operators, delta plus, delta minus. Delta plus is called the upper Laplacian, delta minus is called the lower Laplacian, and the upper Laplacian is essentially going back from d minus 1 form through the co-boundary operator up to D form, and then applying the boundary operator going back to a d minus 1 form. And similarly, for the lower Laplacian, you start from a d minus 1 form, apply the boundary operator, go down to a d minus 2 form, and then go back to d minus 1 form by applying the co-boundary operator. Okay, so what we want to know in this case is the spectral gap, which is the smallest positive eigenvalue of this operator. Okay, so actually what I'm going to argue quickly about is that effectively what we're interested in is spectrum of delta plus, okay? And why is this the case? This is the case because one can show that the d minus 1 forms actually satisfy what's called a Holz decomposition. And basically, you can show that the D-1 forms, the space of the D-1 form decomposes a direct sum of the kernel of the boundary operator and the image of the D-2 co-boundary operator. Furthermore, this set is part of the kernel of the D-1 co-boundary operator, which means that effectively delta minus goes away, okay? Because if you follow the Hauss decomposition, the part that belongs to the image of delta D-2 belongs to the kernel of delta D, of delta D-1, and therefore this bit disappears. Okay, so essentially, we need to focus on the positive eigenvalue of delta plus on the kernel of the boundary operator of dimension D-1. And now the good thing about this is that if you do the algebra and expand this boundary operator, essentially it's something that looks like the Laplace operator of the graph. So here you have the bit that corresponds to the diagonal matrix, which actually is the diagonal matrix of co-degrees. Okay, so here instead of degrees, vertex degrees, we have co-degrees. That is to say, for a D-1 phase, we have the number of D faces that contain sigma, minus something which is not exactly the adjacency matrix, but looks like that, except for the fact that we have an alternating sum. Okay, instead of a sum over all neighbors. Okay, so now what about expansion? What about the relation between the spectral gap and expansion? Okay, so in this case, one could define the Cheeger constant of the complex as follows. So you take the set of all partitions of the vertex set. So this is a K0, the set of all zero-dimensional faces of K. That is a set of vertices, and you partition it into D+1 non-empty parts. And here we have this ratio that kind of looks like kind of the Cheeger type ratio that I showed in the case of graphs, except that here we have all D faces that kind of respect this partition. Namely, they have exactly one vertex in each of the D+1 parts. Okay. And a few years ago, Brzezinski, Rosenthal, and Tesler showed that for any finite complex K with a complete skeleton, namely everything, like all subsets of size up to D R faces, okay, we have this inequality, okay, which actually generalizes generalizes the Cheeger inequality to this context, okay. And of course, what one would hope for is to have a lower bound, which kind of generalizes the lower Cheeger constant, Cheeger inequality in this case, but actually they argue that this is not true. But what they conjecture is that an inequality like that would actually need some constant here and some function, okay, that depends on the maximum co-degree in K. Anyway, so what I'm going to focus on is the spectral gap of the Lineal-Meshulam random complex. Okay, what is this? This is nothing but essentially generalization of a GMP model in the world of the simplicial complexes. And here, okay, we start with the ground set, say with the numbers 1 to n. All possible phases of dimension up to d-1 are present. And what is random is the following, is that if we look at any subset of size d+1, then this becomes a d phase, namely it's present in the d-dimensional complex with probability p independently of every other subset. Okay. Of course, if d is 1, this is just GMP. Okay. And in fact, Linial-Meshulam in 2006 proved a result which kind of generalizes what is known as the connectivity threshold in GMP. So in fact, they showed that if you look at something that's called the first cohomology group, which I'm going to define in a minute, then if P exceeds this 2 log n plus a little bit, omega is an arbitrary function that tends to infinity as it's a function that tends to infinity as n goes to infinity arbitrarily slowly. So if you're a little bit above that over n, then the cohomology group becomes trivial. If P is 2 log n minus a little bit divided by then this is no longer true. As I said, this in some sense generalizes the connectivity transition with GMP in the sense that what's called a cohomology group actually becomes reduces to whether the graph is connected. I'm not sure whether there's any combinatorial interpretation for higher dimensions. But higher dimensions, actually, this was generalized later on by Meshulam and Waller and Gunnar Wagner in the sense that they went to higher dimensions and also they generalized the group over which cohomology is taken. And again, in this case, the threshold for general D becomes like D times log n plus a little bit divided by n versus D times log n minus a little bit. Okay, what is a cohomology group? The D-1 cohomology group is defined as the kernel of the cobinary operator D-1 divided modulo the image. Okay. In fact, what is happening in the subcritical regime when we're just a little bit below the threshold minus increase in function, actually, in this case, there's a phase, a D-1 phase of co-degree 0, which is what happens in the connectivity case, in GMP, I mean. Okay, so the main result we proved together with Mikkel is that when we're in dimension 2 or more and we are supercritical, and when I say supercritical, I mean we are an 1 plus epsilon factor above the threshold, then essentially the spectral gap and the Cheeger constant of the random complex are equal to the minimum co-degree of the complex. And in particular, the minimum co-degree of the complex is logarithmic and is equal to 1 plus epsilon a d log n, where a is a solution to this equation, plus minus a term that's case like root log n. Okay, so this is our first main result. So let me talk a little bit about the proof for a couple of minutes. Okay, so of course you may ask, what is the situation in the case of random graphs? Well, actually, this result was proved some years ago by Kolokholnikov, Austin, and von Brecht. And in fact, they showed that the spectral gap of the combinatorial Laplace operator is essentially the minimum degree of GMP above the connectivity threshold. And in fact, we generalized their result for the minimum degree. And this is how we derive this expression. So basically, this is nothing but a first moment argument together with large deviations for the binomial distribution. Okay, so okay, this inequality here is a theorem for Zonchevsky et al. That I just talked about a couple of minutes ago, and this upper bound essentially would follow if you take I mean, if you consider one of the partitions, namely the partition that corresponds to the minimum co-degree of the complex. Okay, so if you take a d-1 phase of minimum co-degree, and you take a partition where all parts, like the first d parts, are the vertices of this phase, and the rest is what is left over, we get this this upper bound. Now for the lower bound, so this this bit here, things become slightly more complicated, and in this case we use what's called the link graph in complex. So if you have a phase, okay, let me show this picture. This is for a two-dimensional complex. If you take a phase tau that has dimension 2 less than the dimension of the complex, then the link graph is a sort of all edges, actual edges now, that complete this d-2 phase into a d phase. Okay. And in this case, what we need to show is that this infimum, okay, so we use a variational form for the spectral gap, is at least the minimum degree. Okay, so in this case, what we do is that we build upon a result, this old result due to Garland, through which we're able to decompose the Laplace operator into actually graph Laplace operators for the link graphs, okay, or the complex. And after some algebra, essentially we write this this inner product as a sum of inner products. Where we have here the degree matrix of the link graph and minus the adjacent matrix, the link graph, applied to what? Applied to a projection of a form f in the neighborhood of a phase tau, of a d-2-dimensional phase tau. And then we show that this bit satisfies this minimum degree times f dot f. But the other observation is that if you look at the adjacent matrix of the link graph, essentially, not essentially, is actually distributed as a GMP random graph. Okay. And moreover, if you look at the projections of an f of a d-1 form that is in this subspace, that is in the kernel of the boundary operator, then essentially this condition translates into being perpendicular to the old one's vector. Okay. But for this, we have an upper bound on such bilinear forms which are of order root NP, that is root log n in this case, that is due to phi, G, and OFEC. And then we take a union bound over all d-2 faces, and we get this. This is our lower bound. Okay, so this is like a schedule of proofs. And I think I should stop here. Okay, so I'd like to thank you.
Thank you. So let us thank Nikolaos.
Thank you.
Okay, we have some time for a question or two, maybe.
So maybe it's Konstantin Avrachnikov. Maybe I kind of use my question to ask about the second part. Actually, I was very interested in random walk interpretation. So if Nikolaos said a few about random walk interpretation, that would be nice.
Okay, so for random walks, actually, we have another theorem which I didn't talk about, but I can talk about it.
But it's random walk. So it's random walk on faces, or just maybe what kind of random walk you consider?
Yeah. So for random walks, actually, you can generalize random walks on graphs to this context, and essentially here one can walk between d-1 dimensional faces. Okay. So basically, you want to walk from phase sigma, d-1 phase sigma, to another d-1 phase sigma prime if these belong to a d phase of the complex. Okay. Now and basically you can transfer all these notions for random walk in this context. You can talk about stationary distribution and so on, like in this slide. Okay, and for this random walk, we're able to show that if you look at the conductance, okay, because I mean in a random walk like this, you'll be interested in on the mixing time, right?
Yes.
So one way to show that this random walk is rapidly mixing, actually I should say lazy random walk is rapidly mixing, is to show that the conductance is bound away from zero. And this is something that does indeed hold. Again, when you're above the connectivity threshold, the generalized connectivity threshold, so to speak. So it's like in the screen, if you can see the theorem. So if you're above this d log n by 1 plus epsilon factor, then the conductance, the associated conductance of this random walk is bound away from zero.
And so if I just quickly ask another follow-up question, do you think there's a feasibility to consider random walk on smaller dimensional faces? Is it possible, do you think, to say something analytically about this type of walks?
Okay, in this case, and this is not. I'm not sure actually how you define it. I mean, presumably you could extend this in the same way, but I'm not sure whether.
Well, for graph for ages, right? The most like down level, the first level would be on the skeleton, right? Random walk on the skeleton.
Mm-hmm. Yeah, I mean, you mean on vertices? Yes,
on vertices and then on higher constructions.
Okay.
I think definitely these things were considered this kind of up random walk, down random walk, when you basically start from a K phase, you go to a K+1 phase that contains it, and then you go down to another K phase that is contained in that one, or downwards. So first you go down, low end level, and up. And I think these things are quite well studied.
Okay, so I might write an email with reference request to you, Andrei. Thank you.
Yes, sure. I'm not an expert by no means, but I'll find something. Yes.
Okay.
Thank you to Nikolaos.
But essentially what I'm talking about is this concept, right? So like you basically move from d-1 phase to d-1 phase if the two phases are in a d phase. Okay.
Yes, for some specific.
Okay.
Okay.
All right.
Okay.
so
Anyway,
there's
it was a
some-
good extended answer. Thank you.
Just
Okay.
a quick comment, if I may.
There are some questions in the chat.
Can I have a quick comment?
Yeah,
Mhm.
sure.
Yeah, so if you're interested in this kind of random walks, I suggest looking for high-dimensional expanders when the literature also deals with these walks.
Okay.
So actually, maybe Yuval is the right person to for a good
Or maybe
reference.
so somebody can drop references in the chat, right? So if somebody knows the references, just drop references in the chat.
Yeah, Yuval, if you know something, you can do that. And also, I suggest one more thing, Nikolaos. Since you haven't been able to talk about everything you wanted to, you can just send us the slides and we can put it on the website of the conference,
I will,
so that people can take a look at it.
And also, there's another question in chat by Yogesh. Whether
there are two actually.
Oh, okay. I see one.
Replay and
about random flag click complexes that I don't know of, to be honest.
Yeah,
and
so,
then, whether the
yeah,
Laplace
you used
operator has
it.
a special name. I don't know. I mean, this is what's called the combinatorial Laplace operator. Okay. And there's another Laplace operator which might have seen, which is called the normalized Laplace operator. It's essentially the identity matrix minus essentially the transition matrix of random walk. Okay. But I'm not sure about the term you're using here. I don't think I've seen that. Okay.
Okay, I think it's time to finish, and let us thank Nikolaos once again.
Thank you. Thanks.